Swayam Prabha. Digital India. Educated India.
The second talk or second lecture will be on scalable machine learning. Okay, so so you already have a background on optimization, everyone. So so one of the earlier talks in this school was optimization. Okay, so you know all about optimization, right? So very good. So we can, I think. So I will skip. So you know what is optimization, and you know why we care about optimization in machine learning. Okay, and you know what is convex optimization. Okay. Uh, okay. So for example, you have the loss in the top of the screen is the SVM loss or the support vector machine loss. Okay, and the loss in the bottom of the screen is the loss for the binary logistic regression. Okay, and this diagram shows the two losses, and you can understand that both of them are convex losses, right? So both of them are convex losses. Okay, they are convex in X. Okay, and so Lagrangian was covered. So all of you know about what is Lagrangian, what is the dual formulation. Very good. So and then you know about the gradient descent, right? So gradient descent, you basically take a step in the negative gradient direction because that is the steepest descent direction. Okay, and you also, so Newton's method you need not understand. Now has subgradient been covered? Okay, so so just quickly, this is a sort of an extension to gradient for non-differentiable functions. So hinge loss being one very very good example. The other example, so can you understand why hinge loss is not differentiable? The SVM loss, the loss for the binary SVM or many other losses. Do you understand why it is not differentiable? It is not differentiable because if you go back and see the loss, basically it says that there is this portion where if your sort of your x, which is in this case yi times W transpose xi, W transpose xi is the score and yi is the sign, and the product should be, for classification to be correct, yi times W transpose xi should be positive, right? So if it should be positive, but if it goes towards negative side, you start getting more and more loss. Okay, so that is what it is. But until the time it reaches something like 1, okay, there is no loss. So the loss is 0, and then so this part is all flat. So this part is all flat. You can see this part is all flat. Okay, okay, and this part is all linearly increasing. So this is the loss. Okay, and this is the point of non-differentiability. Okay, so can you give one other example of non-differentiable objective that you find in machine learning? Anybody can give example? So how many of you have seen this L1 norm regularizer? You have heard of lasso, right? So L1 norm is differentiable. L1 norm is also a non-differentiable, right? Because where does the non-differentiability come? when it is 0. At 0, yeah, so the norm is like a V-shaped thing. Okay. So these are two very common examples of non-differentiable components that come in the loss function. Okay. And if that is the case, and these are convex. So there are many other non-differentiable things, but these are two convex non-differentiable things. So they look like what is shown in this figure, and still on these you can use something like a gradient descent. Okay, and how can you use the gradient descent? You can use it using this what is called a subgradient. So what is a subgradient? Subgradient is something like the blue line. Okay. So if you know the gradient for a convex function always extrapolates a point to a lower value, right? So if you compute the function value at the extrapolated point, okay. So you understand what is extrapolation? I hope you understand. Okay. So if you compute the function value at an extrapolated point, and if you compute the extrapolated value, linearly extrapolated value, then the linearly extrapolated value always for a convex function is lower than the function value. That is the definition of the function value. And hence, what you know is that it is like a tangent, it is like a lower tangent to the function. So here also, all of the points, instead of going into mathematical definition, so mathematical definition is written here, you can see, okay, which is basically the same. So all the slopes g, okay, of this blue line, okay, so the slope defines the line, okay. So all the slopes which sort of underestimate the function by an extrapolated value is the is part of what is called a subdifferentiable, and basically it is a subgradient. Okay. So subdifferential is the set of all subgradients. Okay. Okay. And if the function is differentiable, then there is only one subdifferential. Okay. Only one element in the subdifferential, which is the gradient. So the subgradient becomes the gradient. But if the function is convex and non-differentiable, there may be infinitely many subgradients. Okay. So in this case, you can think like all this kind of lines, this kind of lines, all the lines which sort of underestimate the thing will be subdifferentiable. Okay. Or will be subgradients rather. Okay. So, I introduced this subgradient descent algorithm, which is the same as the gradient descent, except that here there is no line search as such. Okay. So your step size eta t is typically chosen according to a fixed step size rule. So eta t, you can think it is just typically like yeah. So your eta t is typically could be just 1 by square root of t. Okay, so this is your eta t. Okay. Okay. And so this is your subgradient descent. So it is like gradient descent, but you choose the step size in a fixed step size manner. I will come to the other things. Okay. Now what you know is that in case of machine learning, many a times the actual loss that you want to minimize is the expectation of some quantity, right. So the expectation of loss, so typically let us say x is the sample and y is the label, and you have like h of x, and your loss is something like a function of h of x and y. this is for every example, and now many of the machine learning formulations, they say that if you draw examples IID from a background distribution, the expected loss is what you really want to minimize, but what you end up minimizing is the empirical version of this loss. But that assumption is there that there is an underlying distribution according to which you are taking an expectation. Okay. So, this problem is also called a stochastic optimization problem. Okay. So, all your maximum likelihood kind of so gradient descent on maximum likelihood is essentially doing this. Okay. So, it is taking some samples I is equal to 1 to n, it is calculating the loss on these xi and yi, it is taking the average gradient, that is the gradient of the expected loss, and then it is taking a step in that direction. Okay. So, and this goes for subgradient also. Okay. So, subgradient has all the properties. So, for example, subgradient of some functions is the sum of subgradients of those functions. So, it has all the properties that a gradient has, except that it is not unique. Okay. Okay. So, so now, so for some applications, what people figured out is that this gradient descent is very bad. Okay. And why is this bad? This is bad because your n is very large. Okay. So, your training set is very large. Okay. And which is in one sense good, because then you have a good predictor. Okay. Because your estimate of the average loss is very good, and then if you minimize a good estimate, you get a good predictor. Okay. Which is why if you have a large training data set size, you get good accuracy in the test data, right. But the flip side of it is the optimization becomes slow. Okay. So, how can we still have large data, which is the big data, and or large training data, but not have the problem of slow optimization? Can we have that? Okay. And that is the sort of the idea behind stochastic gradient descent. By the way, has stochastic gradient descent been covered already? Okay. It has been covered? Yeah? Okay. Yeah, okay. Okay. So, this is what is gradient descent or subgradient descent. Okay. So, this is the gradient, this is your gradient, and this is the stochastic gradient descent. So, what is the difference? Right. So, you see, you have gotten rid of this summation. Okay. So, now every update in this stochastic gradient descent, sometimes also called an epoch, okay, every not epoch, sorry, every update, think about it as an update. Okay. So, every update in this stochastic gradient descent takes, in this case, the pure stochastic gradient descent, only one training data point. Okay. And it computes the gradient of the loss at that training data point. So, only the subset of the loss, and then it does the update. Okay. But it does it many times over different training data points. Okay. So, here this is also done many times, but every update here costs order n time at least. I mean, if we assume the dimension and everything to be constant, okay, but here every update costs order 1 time. Okay. Now, what is the, so obviously this is, anyone will say in terms of, you know, you can do much more number of updates. Okay. Question is, how many updates do you need to do? If you need to do order n many more updates in this case, so clearly this update is more noisy than a gradient descent update, okay? Because instead of computing the gradient, what you are computing is the stochastic gradient. Stochastic gradient means a sample, the gradient at a sample point, okay? So a stochastic sample of the gradient, if you will, okay? As opposed to the whole gradient, okay? Now, um, so so it turns out that so another way of thinking about it is also that it is like an online learning. So another way to think about it, since your training data set is a random sample from the underlying distribution, instead of randomly choosing, you can go one by one. Okay, so you have already randomly chosen a training data set. Okay, so you can go sample by sample. So you can go the first sample, second sample, third sample. Every time you do the update. Okay, so you compute the gradient at that sample, you do the update. You compute the next gradient, you do the update. You keep going like this. Okay. So you do this until it converges. Okay. So how do you think? Okay, this is done. So so what is so remember, you have to minimize the original loss, right? So if you if you do a gradient descent, okay, what happens to the loss? Over the updates, also called iterations, it decreases, right? It decreases. So do you think if you do stochastic gradient descent also the losses will decrease? So what happens, let me see this, oh, I have it in the other file. So let me show you what will happen, what you will observe, okay? So what you will observe, so if you, so remember here you are plotting the whole loss, not the stochastic loss, okay? On the y-axis you are plotting the whole loss, and here you are doing stochastic updates. Okay, 1, 2, 3, 4 and all this. So what you will see is a plot something like this. Okay, so it is sort of converging. You can see that it is sort of converging like this. Okay, it is sort of converging like this. Okay, but you will not be able to tell. Okay, why will you not be able to tell? Let me tell you that a typical run, okay, so so long as you choose the data points randomly, a typical run would look like the red curve that I just showed you. Okay, so I mean there will be like very poor runs where you will see something like this. Okay, but that is like the chance of this run coming in a simulation is like very low. Okay, so so this will almost never happen. Okay, almost always you will see what something like this red loss. Okay, so so what is the problem? Why will you not be able to tell? See, if you take two consecutive values, you take this value and you take this value, it has increased. You take the next value, it has decreased. You take the next value, it has again increased. Again maybe this value has decreased a little. Again decreased. So consecutively let us say 3, 4 values it decreases. Again one very large increase. Again another increase. Okay. So if you are observing, so you have to come up with a rule, right? You cannot come up with the algorithm based on the visual inspection. On the visual inspection, you can see that it is converging. Okay. But you don't know, you cannot come up with an algorithm based on the visual inspection, right? So so the problem with this is that you cannot tell. So what must you do? Okay, so let's say you stop at this point. Okay, you say that, oh, I have converged, and you stop at this point. At this point, whatever update you did caused a very high loss, relatively, not this high, but definitely higher than this. Okay, so one thing you can do is you can maintain a running minimum of the loss. Okay, what is the problem with that? The same problem, right? What is the problem?
It is minimum, but it may happen that we can get one more minimum after 10, 20.
No, that anyway can happen. No, I'm saying if you maintain a running minimum, see, one problem can be, one simple problem is that minimum of what? Okay. So, let's say you can say that minimum over the entire training set. But then you are again spending O(n) time to compute the loss, and then only you can take the minimum. Okay, that is what you wanted to avoid in the first place. That is why you did. You don't want to compute the loss at every update. Okay, loss or gradient, whichever. Okay, so then you are stuck. Okay, so people do two solutions. Okay. First solution people do is they take a small validation set and compute the loss on that small validation set. So the update comes from a large training set, the loss comes from a small validation set, okay, and you maintain the running minimum on this small validation set. Okay, this is what is the recommended solution, also sometimes called something like a running cross validation. Okay. The second solution is that you store the last k iterates, okay, and you have something like the average of the last k weights as your final weight. Okay, these are the two solutions. Both solutions you can show converge. Okay, clear? So what you are going to do? So you don't want so the algorithm is running repeatedly. You don't want to compute anything over the whole data set, whole training data set, which is really large, and it is there in the distributed memory and all these things. Okay, so so you do this updates. So you do this stochastic updates, but then if you do this stochastic updates, okay, you get this kind of a behavior, okay, stochastic behavior, and you can sort of combat that by using this either the running minimum on a validation set or the last k average. Okay. Now, so this example you have seen, right? So you have seen some this thing. So sort of this SGD, it was there for a long time, but it was kind of resurrected by a paper, very influential paper by Leon Batu in 2008. Okay, where he showed that you can just solve SVM in 1.4 seconds, whereas for the same problem, like it took like 20,000 seconds or something, or fast SVM took 66 seconds or something. Okay, And the key thing to note here is that so this plot is also a very crucial plot. This is from the same paper. So what this shows is that so if you so x axis is the quality of the optimum. So you, in this case, he computed the actual true optimum. True optimum is the lowest value that the objective function f can have, okay, and he is plotting how much higher this optimum is compared to the true optimum, okay. And if you are fine with, so this is something like the tolerance. You can see the x axis is something like the tolerance, okay. So if you have a high tolerance value, like if you have a tolerance value of, let's say, 10 to the power minus 4, okay, you see your SGD takes much less time. So your y axis is time, so it takes fraction of seconds, whereas this guy takes something like a 25 seconds, okay. But if you want a very, very accurate solution, like you want to within 10 to the power minus 8 accuracy, okay, so your tolerance is 10 to the power minus 8, then you see that suddenly this stochastic gradient descent will take much, much more time to compute it than the normal. Now what Leon Botti argued correctly is that most of the time your f is a proxy for the true f anyway, okay, because it's a stochastic optimization problem. You don't know, you think your training samples are sacrosanct, but they may not be sacrosanct, okay. They are just samples from an underlying distribution. If you had collected the training data set on some other day, it would have been some other set, okay. So you are fine with 10 to the power minus 4, 10 to the power minus 5 type solutions, okay, and which is where SGD really shines. Clear? So with very few number of updates, you can get a reasonable accuracy, but you cannot get a very high accuracy with SGD. Okay? This is number 1. Okay? Okay. So now another thing is that yeah. So when you implement this in a distributed manner, so here it is not there probably. Okay. So when you implement this thing in a distributed manner, okay. So the updates. So if you use just a single data point, the update becomes too noisy. Okay. So you can solve that problem by using what is called a mini batch SGD, okay, or mini batch stochastic gradient descent. So what is a mini batch SGD? Mini batch SGD is one where instead of, you still use a stochastic gradient, but instead of computing the stochastic gradient using just one data point, you compute using a batch or a mini batch of data points. Okay. So you compute the average gradient, or so typically it's an averaged loss. So you compute the average gradient of a mini batch of data points. Okay. How do you compute? So that is typically seen to be improving on. Okay. Okay. So that improves or reduces the number of iterations that you need. Okay. Now, how will you do this mini batch SGD in a distributed manner? So we again come to our big data setting where the training data set is distributed on many servers. Okay. And you want to compute the mini batch you want to run the mini batch stochastic gradient descent in a distributed manner. How do you do this? So, a simple way of doing this is, let's say you have k servers. So, can you tell me what is the disadvantage of stochastic gradient descent on big data? Validation set, yes, but the bigger disadvantage on big data of stochastic gradient descent is that it is strictly sequential. Can you parallelize this stochastic gradient descent algorithm? If you remember the algorithm, can you parallelize this algorithm? So, you have now data on many machines, you can use many machines, so you would want to parallelize this, right? Can you parallelize this algorithm? So, the answer is not very easily. There have been many attempts, but it is more or less understood that stochastic gradient descent cannot be parallelized very easily. Remember gradient descent, can you parallelize gradient descent? But I just showed in the last lecture the gradient descent, parallel version of that. I just wrote in Spark. Huh? So, you can very easily parallelize gradient descent because your gradient computation can be parallelized. But here, if you are computing the stochastic gradient, each example is on a different machine. So, if you are computing it using one example, okay, you are only using that machine, you are not using any other machine. And then you cannot do another update unless you do this update, because the updates are sequential one after the other. Okay. So, hence stochastic gradient descent is not very easily parallelizable. Okay. So, then what happens is that so one way of parallelizing stochastic gradient descent is using mini batches. And how do you use mini batches? What you do is you take maybe one example from each machine, one random example from each machine, and construct a mini batch. Okay. So, let us say you have 100 machines, so you construct mini batch of size 100 with one example from each machine. You compute the gradient on that example, and then you compute the aggregate gradient. Okay. And then this is the gradient on the stochastic mini batch, okay, or stochastic loss on the mini batch. Okay. And then you update using this. So, is this clear? So, if you have like gradient, let us say delta 1, delta 2 till delta k. So, your mini batch gradient delta is going to be 1 by k summation over I is equal to 1 to k delta I, and then you run something like w k plus or t plus 1 is equal to w t minus eta t delta bar t. Next time again have another sample of mini batches and run it. Okay.